And there you go. Two hydrogens, one oxygen, all locked together by sharing. We've got a single, stable H2O molecule. Now, you might think, okay, it's funny. We see it, touch it, drink it every single day. Water. It's got to be the most common thing on Earth, right? But it's also one of the most extraordinary. Because locked inside this simple little 3-atom molecule is a design so brilliant, it's literally the foundation for all life as we know it. So today, let's peel back the layers and really look at the incredible architecture of water. Which brings us to the big question, the one that drives this whole explainer. Why water? I mean, think about it. Of all the molecules out there, how did this one, H2O, become the absolute basis for everything that lives? It's a huge question. And the answer, well, it's not just some boring fact, it's actually a story of incredible, elegant design. And that's the journey we're going to take together. Okay, so to really get this, we've got to start at the beginning. Just like any good recipe, right? We need to look at the ingredients, the individual building blocks. And for water, it all kicks off with two of the most fundamental elements you can find anywhere. So you've got a tale of two atoms here. In one corner, we have the heavyweight champion, oxygen. It's a pretty big atom, with 8 electrons buzzing around. And in the other corner, hydrogen, the lightest, simplest element there is, just one single electron. Now, this difference in size and, the number of electrons, it's everything. It's absolutely crucial. A good way to think about it is like oxygen is the big kid on the playground with a super strong gravitational pull, while hydrogen is the smaller kid. And this difference in pull, that's the first major clue to understanding water's power. Right, but these atoms just floating around by themselves, that's not water. The real magic happens when they connect. So let's get to the fun part, the assembly phase, and see how they actually bond together to build this molecule. And the way they do it is through something called a covalent bond. What's so cool about this is how simple the idea is. Just think of it like two people holding hands to stick together. It's not about one atom stealing an electron from the other. Nope, they just agree to share. And this sharing creates this really strong, really stable connection. And boom, you've got a brand new thing, a molecule. So here's how it plays out. That big oxygen atom, it needs 2 more electrons to feel complete, to be stable. And what do you know? Each of our little hydrogen atoms has 1 electron to offer. So the oxygen atom reaches out and holds hands with 1 hydrogen, sharing a pair of electrons. Then it just does the exact same thing with the second hydrogen atom. It's this perfect cooperative deal that makes everyone happy and creates a super sturdy molecule. And there you go. 2 hydrogens, 1 oxygen, all locked together by sharing. We've got a single, stable H2O molecule. Now, you might think, okay, job done, story's over. But honestly, the most mind-blowing part of this whole thing is just getting started. Because it's not just what it's made of, it's the shape it takes. This is where we get to its most important design feature. See, the atoms don't just line up in a perfect straight row. They form this weird, kind of lopsided shape. And that arrangement, that little bend, is the secret sauce to almost everything water can do. But why, right? Why is it bent? Why isn't it just a straight line HOH? I mean, that seems like it would be way simpler, more symmetrical. But nature's a lot more clever than that. This bend isn't some mistake. It's a feature, a critical one. Okay, remember how we said oxygen has that stronger pull? Well, that's the key. Even though it's sharing electrons with the hydrogens, it's not sharing them fairly. It's kind of hogging them. So the electrons spend way more time hanging out near the big oxygen atom and less time around the hydrogens. And this unequal tug-of-war is what actually pulls the hydrogen atoms in, creating that very specific bent V-shape. And this lopsided shape creates a property called polarity. Now, don't let the word scare you. The easiest way to picture it is that the water molecule basically becomes a tiny little magnet. It's got 2 different ends, 2 poles. One end is a little bit positive, and the other end is a little bit negative. It's not like a battery with a full charge, it's more like it has charged zones. And here's what that looks like. Because all those negative electrons are crowded around the oxygen, that side of the molecule gets a slight negative charge. And since the electrons are being pulled away from the hydrogens, their side gets left with a slight positive charge. So one molecule, 2 different personalities, a negative end and a positive end. This is so important. Okay, so let's zoom out. A single water molecule is cool and all, but a glass of water has trillions upon trillions of them. So how do all these little tiny magnets interact with each other? This is where the whole thing becomes incredibly powerful. They stick to each other using something called a hydrogen bond. And it works exactly like you think it would with magnets. Opposites attract. The slightly positive hydrogen end of one water molecule gets drawn to the slightly negative oxygen end of a neighboring water molecule. This attraction is the glue that holds liquid water together. Now, it's way weaker than the bond holding the molecule itself together, but its real power comes from the fact that there are just so many of them. Just look at how this plays out. One molecule lines up to attract another. That new one then turns and attracts another, and another, and another. It creates this incredible, constantly changing network of connections. In just one drop of water, every single molecule is connected to its neighbors through these quick but super effective hydrogen bonds. And this is the whole point, right here. It's this huge, interconnected web that gives water all of its incredible, almost magical abilities. Scientists call them emergent properties, which is a fancy way of saying these properties don't exist in just one lonely molecule. They only appear, they emerge, when you get trillions of them all sticking together and acting as a team. All right, so let's bring this all back to the real world. How does this whole system, this bent magnetic molecule held together by these hydrogen bonds, how does that actually create the liquid that shapes our entire planet and everything inside of us? Well, this network leads to some amazing stuff. You get cohesion, that's water sticking to itself, which is why you see beads of water. You get adhesion, that's water sticking to other things, which is literally how plants can pull water all the way up their stems. It's got a high specific heat, meaning it takes a ton of energy to heat it up. That's why cities near the ocean have more stable temperatures. And then there's the big one, its role as the universal solvent. I mean, just think about it. When you stir sugar into your coffee, where does it go? It disappears, right? Well, that's because the positive and negative ends of all those little water molecules are literally grabbing onto the sugar molecules, pulling them apart, and surrounding them. This single ability to dissolve stuff and carry it around is fundamental to life. It's how your blood transports nutrients and how your cells get everything they need to function. So it really all comes full circle, doesn't it? We started with just two simple atoms. They hooked up with covalent bonds to form this bent magnetic molecule. Then millions of those molecules used hydrogen bonds to create a massive network. A network that can climb trees against gravity, that can regulate the entire planet's temperature, and that can power every single chemical reaction happening inside you right now. It's amazing. From the simplest possible starting point, you get the most profound complexity. And it really makes you wonder, if all of this incredible, elegant complexity is hiding inside a simple drop of water, what other secrets are just waiting to be discovered in the basic building blocks of our universe? It's something to think about the next time you pour yourself a glass. Thanks so much for diving in with me on this one.